So what information can we get from a reduction potential table? So usually you encounter this table. So a reduction potential table is the potential that you have when you have a reduction reaction. So the arrangement can be like this, from more positive going to more negative. In other instances, you can have the more negative here going to the more positive. But the thing that you need to remember, okay, the higher, okay, or the more positive the reduction potential, okay, the more likely that reaction will remain in the reduction form. So what it will do, the reduction reaction that has lower reduction potential, okay, will be oxidized. Now, another thing that you have to remember, okay, following the acronym LIORA versus GEROA. So if you're not sure about this, so this is loose electron undergoing oxidation and reducing agent. And then this gain electron undergoing reduction, okay, and oxidizing agent. So what does it tells us? Okay, if this undergo reduction, so that means this species here is an oxidizing agent, okay? And the species that form here is the so-called reducing agent. Now, the way that we can look at the trends of this increasing strength of oxidizing agent is the more positive that you have, okay, the more likely, the stronger is the oxidizing agent. Now, for the reducing agent, usually is the metallic form that assume it, okay, and the way that you're going to look at it, okay, the more negative your reduction potential, the stronger is the reducing agent. So you can ask the question here, which is the strongest oxidizing agent? So if we're going to look at here, okay, the answer there would be the gold, okay? And which is the weakest oxidizing agent? So the one that we can have here is the Na+. So you have to put the charge, okay? So when we're talking about reducing agent, so usually it's a metal. So if we're asked which the strongest reducing agent, usually we could say that's the Na, the sodium metal, and the weakest reducing agent, that's what we call the gold. Now, what other information that we can have from here? Another information that we can have here, let's say I highlighted here the silver. So what does this silver mean? So anything below the silver, okay, anything below here, mercury, iron, copper, chromium, sodium ions, they can be oxidized, okay, by the silver. So the metal that they have there, or the more, the lower oxidation number that they have there in their form, they can be oxidized because silver is a stronger oxidizing agent compared with this one, but it is a weaker oxidizing agent compared to the other one. So the same thing if we have the silver metal. Okay, so we have the silver metal here, it can reduce, okay, anything that is higher in the reduction potential here, like gold, okay, the two forms of gold, okay, but it cannot reduce the one that is lower than it, okay? So that's the information that you can get. Now, you can also get information here if you're asked what's the cell potential. So we all know, okay, that it is just between the cathode minus the cell potential of the anode. So if we are asked, what's the cell potential, let's say, between silver and chromium, okay? Or a voltaic cell that is made up of silver and silver ion and chromium ion. So based on the reduction potential, the higher that you have there, so that's 0.80, and then we subtract it with chromium, which is negative 0.74. So what we have here, we're just going to look at the difference. So we end up with 1.54. volts. Now, if you are asked about the electrolytic cell between silver and the chromium system, so the way that we're going to work on the system is your cathode here, okay, will be made up of the negative one, which is negative 0.74, and your anode will be made up of the more positive one. Okay, and what you're going to get here is a negative value. So a cell potential that is positive, that is a voltaic cell, and it's a spontaneous reaction. A cell potential that is negative, that's an electrolytic cell, and it is non-spontaneous. You need energy to make the reaction happen. Okay?